Hello and welcome to this video where we're going to talk about the geometric distribution. We have already discussed the binomial distribution. If you haven't seen it, there's access through it via my playlist on probability statistics 1 videos. I am almost done with the series, so I hope to get soon the one on normal distribution, and that will be covered the entire paper, as well as the link in the description that gives you access to my web page where you will find more explanation and exercises through it. We were talking about the fact that distributions can help us model scenarios where the situation is either success or failure. And we were talking about the fact of getting a 6 when we roll a die. The binomial distribution was used to count how many sixes we get in independent rolls of a dice. In this case, what we're going to be doing is we're going to count how many rolls we need until we get our first 6. So, for example, if I only needed one trial, it's like, okay, I get a 6 in my first in my first try. That means that the probability is 1 out of 6. Okay, the probability of getting 6 in my first trial is just 1 out of 6. But then if I needed 2 trials, that means that in the first one I didn't got a 6 and then I got a 6. So it's 5 out of 6 times 1 out of 6. If I do it in my third trial, that means that in my first 2 attempts, I didn't get a 6, and then I get a 6. So it's 5 out of 6 raised to the power of 2 times 1 6. And if we keep on going, I believe that you can see the pattern now. The probability that I get my first 6 in my xth attempt is not getting a 6 until the x minus 1th attempt, and then getting a 6. This is how the geometric distribution works. So, which are the conditions for a variable to be geometric distribution? Well, we have repeated trials, and we're only going to have one parameter. That's going to be p. So, we have repeated trials that are independent. In this case, we can think of in infinite trials. That's not going to be a restriction to our thinking as it was when we had the binomial. It's not going to be now in the geometric. And again, we have only 2 possible outcomes, success or failure, and the probability is always the constant. So what we're doing now is we are getting a variable that counts how many trials we need to get the first success. That variable is called, that is distributed geometrically, and we write it like this. X is distributed as GOP, and the formula to calculate the probability that is also given in the list of formula is probability that x is equal to x is 1 minus b raised to the power of x minus 1, meaning that in every previous attempt to x we don't get a success, times b, meaning that we finally got a success. So it's just the interesting thing about the probability the geometric distribution is that we can also get some other formulas that will help us to understand and solve some other problems. For example, if we are going to work with probability x or equal less of x less or equal than a value of x, that means that we are having success on any of the first X trials. Okay, on one of our first X trial. It means that my success is before that. And that is complementary of having failure on my first X trials. If I had a success on any of my first X trials, that means that I didn't fail on the first X trials. But failing on the first X trials is failing raised to the power of X. So essentially we can say that the probability of X less or equal than X is 1 minus b raised to the power of X. On the other hand, if we are told that the probability of, we have to find the probability that X is greater than X, this means that the first success was after the Xth trial. that is the same as saying that we failed on the first X trials. And what does failing means? Failing means 1 minus p raised to the power of x, because that was x times. So let's put this into practice and let's see the example that I chosen here for you to show. As usual, if you want more on this, you will find it on my webpage that you can access via the link in the description. We have first, a coin is biased so that the probability of obtaining heads with each toss is 5 out of 11. It's a bit more than a half. So that's going to be my P. My P is going to be 5 out of 11. And we're going to have that the coin is tossed until I get my first head. So yes, my P is going to be 5 out of 11 because the probability of getting a head is 5 out of 11. And we have to find the probability that I could toss the coin at least 6 times or less or fewer than 8 times. So my random variable x is going to be distributed geometrically with parameter 5 out of 11. And I want to find for the first one that the probability of x is greater or equal than 6. Remember that we said earlier, we mentioned the formula that the probability, which write it with yellow, the probability that x is greater than a value lowercase x is equal to 1 minus p raised to the power of x. Remember that x greater to a value means that your first success is after that instance, so all of the previous values were a failure. So that is failure raised to the power of x. Now the thing is, for my formula, I have a less than, and in my question, I have a less or equal than. So that can be misleading. Well, there's a very easy solution around this, because as these are discrete variables, it is the same to say that x is greater or equal than 6 than saying x is greater than 5. You see that? It's the same thing, because if a value is greater or equal than 6, then it has to be greater than 5. This is because these are discrete variables, so they cannot take intermediate values. So these two are the same, and now yes, we can use our formula, because this is now going to be 1 minus 5 out of 11 raised to the power of 5. So we plug that in and we get 0.0483. That's the probability given to three significant figures. I believe, I hope that you can understand that this does make sense, okay? If we're saying that we have to toss the coin at least 6 times, this means that I failed my first 5 times. So I failed my first 5 times means not my probability to the power of 5, okay? I hope that that makes sense to you, because if that makes sense to you, then the problem becomes easier. But if not, then it's just applying formulas. It can be a bit messy for you to understand at first. Then what happens with the second exercise? For the second exercise, again, we're going to be using the other rule, that is the probability that x is less or equal than a lowercase x is 1 minus 1 minus p raised to the power of x. And in this case, what we want is that the coin is tossed less than 8 times. Less than 8 times means probability of x greater, less than 8. Again, we have a problem because my formula uses less or equal and I'm just given less than. But we can solve it using the idea of discreteness. If a value is less than x, then the value is less or equal than 7. So we can use the formula using my lowercase to be 7. So in this case, I'm not going to write p because I have the value of p. My p is 5 out of 11. That's 5. And I'm going to raise that to the power of 7. I'm going to plug that into the calculator, and I'm going to get 0.986. Again, let's try to understand this so that it's not just applying formula, because these formula are not given to you. So you need to either memorize it or understand it. how can you understand this? Well, the probability that I tossed my coin less than 8 times means that I got a success in any of my first 7 trials. And getting a success on any of my first 7 trials is the contrary of getting a failure on my first 7 trials. Getting a failure is this. This is the probability that I get a failure on my first 7 trials. So the contrary of that is going to be the complement of that is going to be 1 minus that probability. This is why that makes sense, because I'm thinking, okay, yeah, I want to complement the fact of getting a failure. That's what I want. Okay, I hope that that makes sense to you again, so that this is not just applying formula.